So we're in the middle of, or towards the end of talking about how decision trees, or trees in general, can be used for modeling something as discrete and high-dimensional as language. And we saw that beyond the standard problems that you have with constructing trees for general problems, like decision trees and classification trees, there are specific problems that come up because it's language and it has a huge vocabulary, and because what you're trying to generate is conditional probability distributions, not categories or numbers. So it's not classification, it's not regression, it's density estimation. Nonetheless, it can be done with a lot of approximations and shortcuts and heuristics. The result is far from being guaranteed to be the best possible tree. In fact, whenever we do modeling in large spaces, we like to think of the shortcomings of our models along at least two different dimensions. One of them what we call modeling errors, and the other one is what we call search errors. So a modeling error would be that you modeled the wrong thing, that you didn't have some important attributes or features or inputs that are relevant to the answer, that you used an assumption that is incorrect, that's violated in practice. A search error would be different. It would be an error that you make not because the assumptions you made were wrong, but because you failed to find the optimal solution to the setting that you set up. So if you believed in the maximum likelihood formalism in the context of a particular likelihood function, a particular assumption, then sometimes it's easy to find the maximum likelihood member of a set, but sometimes it's hard. And if it's hard, you use heuristics and you don't necessarily find it. And then when you're given a real world situation, you have to take action based on it, be it machine translation or information retrieval or speech recognition or anything. You may have not made the right decision, whereas the true maximum likelihood hypothesis, had you found it, maybe would have made the right decision. Another example of that would be anytime you set up an optimization problem, if you end up with a heuristic optimization, you really didn't fully optimize, and what you end up with makes a mistake, and you can show that the true answer, so if you somehow have a way of deriving it later, would not have made a mistake, you would consider that a search error. In another example of search errors, in the speech recognition, we do a during recognition time, not just during training. During recognition time, we do a very extensive search of a large hypothesis space, and it's full of heuristics and full of shortcuts. And these shortcuts sometimes result in errors. And that's a case where you can prove that it was a search error if you force your search recognizer to recognize the correct answer. If you just lead it by the nose to the right answer, and you calculate the score that the model gives you, and you compare it to the score that you got on whatever it is that the recognizer actually did output, sometimes you will find that the score on the correct output is better, according to your model, than the score on what it gave you. And the only explanation for that is that it failed to consider the correct answer. It just didn't see it because it didn't walk down that path. Excuse me. So I mentioned two kinds of error. Actually, there are three. There is modeling error. There is search error, such that if you had infinite computation, you could eliminate that completely by searching exhaustively over the space. And the third type is what I would call a Bayesian error. A Bayesian error is an error that a Bayesian would make even if they started from the correct prior, namely, I set up the problem, I know what the prior is, I tell them the prior, they use that prior, they have the correct they have the correct likelihood, they have infinite computing power, they can do everything right, and occasionally they will still give me the wrong answer. And the reason is that the underlying categories, in the case of classification, have inherent overlap between them. So a very simple example of Bayesian error. Suppose you know that your data comes out of two sources, source A or source B. And each source is a Gaussian. And you know the mean and the standard deviations of both Gaussians. You know this is mean B and standard deviation B, and this is mean mu A and standard deviation mu A, sigma A. Whether you learned it from lots of data or somebody just told you, you know everything there is to know. There's no more learning to be done. You fully understand the process in which the data is generated. You're also given the prior over them. That's part of your understanding. P of A and P of B, which must sum to 1. So you have a full and accurate description of the stochastic process. The process says, for every data point, choose between A and B with probability P of A, choose A, otherwise choose B. And once you chose whether it's A or B, go to the appropriate mean and the standard deviation and draw randomly from that Gaussian and give me that X. And now, given the X, I need to decide if it came from A or B. That's my classification problem. In that case, in the case where I know all the parameters and I know they're to be correct, I would still make mistakes occasionally. When will I make a mistake? Well, Bayesian decision theory tells us that we should look at where these two cross if PA and PB are 50-50. If they're not 50-50, you would need to scale it. But basically, there would be a point where the posterior for A would go above 50%, and then we should choose A. Otherwise, we choose B. Let's assume for simplicity that they are 50-50, so this point is exactly where they cross here. So this is my decision boundary. My decision boundary is this point, this threshold. So any point that's higher than this threshold, I will choose B. Any point that's lower, I will choose A. Now, if I get a point X, it could have come from A. It could also have come from B. It is more likely to have come from A, so I'm correct to guess A in the sense that it will minimize my error, but it will not bring my error to 0. Sometimes it really did come from B. That's Bayes' error. This is irreducible. It has to do with the fact that the two distributions overlap. I can calculate the posterior. I can make the decision to go with whichever one has the highest posterior, but occasionally I will make mistakes. I cannot do better than that on average. So Bayes' error is a property of the problem that we're trying to solve. If the problem is inherently overlapping sources, the Bayes' error could be high, could be very high. In the extreme case, where the two Gaussians have the same mean and the same standard deviation, there is no way I can do better than 50%, because there's no way of distinguishing them, right? It came from A or from B, but it has no effect on the outcome, so this is a property of the problem, not of my model or my solution. It's irreducible. As long as I didn't change the problem definition, it's irreducible. The modeling error has to do with the difference between my modeling assumptions and the truth, the reality. Generally speaking, the more wrong assumptions I make, the more mistakes I will make, although not necessarily. And the search error has to do with my compromises along the way to optimizing some measure, or in just searching through the space of possible solutions. It's more algorithmic. It is useful when you work on whatever language technology you're working on for your research to think, whenever you're in a situation where you made mistakes, can you ascribe them to one of these three categories? You can't always be sure which one it is. But there are times when in a situation where you can clearly, for example, the example of speech recognition that I gave you, you could clearly identify the search errors. You cannot necessarily tell apart modeling errors from Bayes errors, because there may be ways in which you can fix your model to not make a particular mistake that you made, but it may make the model make other mistakes that it didn't make before. So you plug it here, it opens up there. The Bayes error is the bound on how much you can plug it without, where do you stop? Where is it the case that anything that you plug, something else will open? Basically, the minimum error possible. Questions? Okay, so let's go back to decision trees. I'm sorry, to trees used for language modeling. Yes?
When you think about a language technology, can you think about a human annotation approaching a problem as some sort of a lower bound and therefore basing an error on your model?
It's a great question, a great segue to a discussion of what human ability versus computer ability. What kind of bound do you think human performance is? Is it a lower bound or an upper bound? One could argue that it's neither in the following sense. It is an existence proof. If I'm able to consistently do something well, other than metaphysical argument about my soul and consciousness, if you believe that I do it through information processing, which is the sort of fundamental assumption of AI, then it shows that there is an algorithm and there is hardware that will do it, right? So it's great because it provides motivation and inspiration. It says, hey, it can be done. On the other hand, it may be very far from my current capability with my machine learning algorithms, both because of algorithms and also mostly, I think, personally, because we don't know what's the relevant input. There's so many inputs to people when they do things. So it shows that we might be able to do as well, but it doesn't tell us how. But the opposite is also not true, which is what you were getting at. It's possible that machine could do better than people. There are cases in the world where we're able to do that. Chess is one classic example. And machines clearly beat people, no question about it. It's still useful to look at human error rate as a motivation, inspiration, and proof of existence. So let's take a simple example of topic classification. Let's say there are 20 topics, and I give you each 1,000 documents, the same 1,000 documents, and ask you to classify them as belonging to one of them. You will not all agree. How much you disagree is a very useful measure. It's called the inter-annotator disagreement rate. It's reasonable to try to aspire for our machines to be indistinguishable from people so that my algorithm's disagreement rate with each one of you should be on average the same as your disagreement with each other. That would be a fairly good achievement. Notice that if my algorithm becomes better than all people, I don't have a way of knowing it, right? If I don't know the ground truth. Often, there is no well-defined ground truth. What does it mean for it to belong to a particular topic? Well, in reality, language is a very slippery thing, and it could belong to multiple topics. I just forced it into belonging to one topic. So you can look at inter-annotation disagreement rate as a measure of how clearly the concepts are defined. You can say that if people tend to agree on things 99% of the time, that the concepts are pretty well defined. They're defined to be within 99% accuracy. If you can't get people to agree more than 90% of the time, you can say the concepts are fuzzy. So that puts a limit in that sense, that if you cannot annotate, label the data correctly, more correctly than the disagreement between people, then you don't have a chance of doing better than that. And if you did better than that, you wouldn't know it. Does that address your point? Okay, so back to trees. There was this big experiment in the late 80s of trying to build a language model using a tree formalism. And it took a lot of computation. It made a lot of computational shortcuts along the way, because if you remember, the number of possible questions is doubly exponential, and the order in which you consider them, it's a greedy choice, and there are all these suboptimal ways of going about it, but you didn't have a choice. And when they did that, the one thing that they had in their favor as an inspiration point is that all n-grams are special forms of decision trees, or of trees. You can implement any n-gram as a special tree. So the set of all possible trees is larger, much larger than the set of all possible n-grams, no matter what smoothing method you use. And as a result, it gives you hope that there are members in that set that are outside the set of n-grams that are better than n-grams. If n-grams form a tiny fraction of the set of all possible tree models, then why should we think that that's where you should find the best answer? Certainly there are linguistic considerations that you can express in trees that you cannot express in n-grams. For example, questions that you ask about the general history, not about any particular position. Like, was a military term used anywhere in the history? Was a sports term used anywhere in the history? You can ask these kind of questions in trees. You cannot ask them in n-grams. So the hope was high. The computers were smoking hot. And after months and months of CPU, they created a tree that hopefully if you read the paper, you know, it was a very fancy tree, but did not improve much on n-grams. In fact, it didn't improve at all, if I remember correctly. But then they did what we all do and what I encourage you to do. If you put 2 years' worth of effort into something and it doesn't work, before you throw it in the garbage, interpolate it with an n-gram. Right? And chances are it will improve on the n-gram. Could it make things worse than an n-gram? No, as long as you're, because it's shrinkage, and as long as you're allowing the weight to optimize itself on held out data, you're guaranteed to do at least as well as the n-gram. But when you add something to the n-gram, there's a good chance it'll improve. And it did improve, a few percents. And then I mentioned to you this idea that they had, okay, if we couldn't really do much on perplexity, which is the average surprise or the average log probability, let's see if we can reduce the fraction of the time that we are greatly surprised. They put a threshold at 10 to the negative 4, and they found that indeed they do reduce it. But overall, they were still pretty disappointed, given this was a commercial group that had to transition their technology into a product. The complexity of building trees and of using trees is so much greater than n-grams, they were just not justified. So they let it lay dormant for a while, and then they came back to it, I think, a few years later, maybe 2-3 years later. And they decided that what they did wrong was they searched too large of a space. Still, even though they had to make many restrictions, they still felt that they were searching too large of a space. So their suspicion was that there are trees out there in the land of all trees that are good and are significantly better than n-grams. But they just couldn't find them because they considered such a huge space, they took a path through it and didn't search thoroughly enough. So they decided to take a somewhat different approach and to restrict the space in which they search for the trees. And they decided to do it the following way. First, they said, let's represent every word in the history as a series of bits that gradually refine our knowledge of what that word is. So this required representing words, clustering all the words in the vocabulary in a way that we will talk about in the rest of this lecture. But the idea is that if you create a reasonable clustering of the vocabulary, a hierarchical clustering, so the entire vocabulary is here, and maybe you make a distinction into verbs and adverbs, verb plus adverb here, and nouns plus adjectives here. And then you make a further distinction into verbs and adverbs, and here into nouns and adjectives. And then within the verbs, you'd maybe divide them into past tense verbs and another kind, and so forth. And nouns could be singular and plural, and then you can make some semantic distinctions like abstract nouns, non-abstract nouns, and you keep making the distinction further and further and further and further until you get to very specific categories like days of the week and office workers and university concepts and verbs that mean to give something to someone. And you can make this fine. It's somewhat subjective, but you can make this very fine distinction, and you can put all the words in the vocabulary into some kind of a tree like that. And the nice thing about this tree is that you can now represent every word as a path from the root down to the bottom, all the way, let's say, to the word computer here. So there's a path that goes like this. And it goes quite deep, because if the vocabulary is 100,000 words, the depth of the tree has to be at least log of that. And since the tree is not necessarily balanced, the depth could actually be longer than that, right? Now here's the beautiful part. You can put bits along each split. So you can decide that on the left will be 0, on the right will be 1. On the left 0, on the right 1. On the left 0, on the right 1. And now you can represent every word as a bit string, where the highest order bit is this one, 1, then 0, then 1. So computer would be represented by a bit string that starts with 1, 0, 1, and then a few more. And what's log base 2 of 100,000? 64 is 6, it's 16 and a half, 17. So maybe there would be 30 bits here. You could make do with as few as 17, but you don't want to necessarily insist that that the tree would always be balanced, because there are many more nouns than there are verbs, for example. But the important thing is that now you represented every word by an ordered string of bits that has a very nice property, that the bits are meaningful. The most meaningful bit is the first one, because it tells you whether you are in this category or that category. And then once you know the first one, the most meaningful bit is the one after that. And the meaning of the bits is relative to the bits that came before them. So this 0, because this is 1, and we're here, this 0 means nouns as opposed to adjectives. But if this were 0, the second 0 would mean verbs as opposed to adverbs. So every bit has a meaning, a semantic or syntactic meaning that's conditioned on the bits that came before it. And words that are similar, that tend to be in the same class, either semantic class or more broader syntactic classes, share an initial substring. That's really a beautiful thing, if you love language. Yes?
So the question might not be relevant to this, to what you are introducing, but I just want to ask. So, what happened to the words that have multiple meanings?
Mm-hmm.
So, like,
Yeah.
a word can be a verb or
Right, right. A very good question. So ideally, you want to do this in the space not of words, but of word senses, right? But word sense is not a surface phenomena, it's a hidden phenomena. So you have several choices. You can ignore that and just put the word saw, treat it as a verb, even though it can be a noun, right? Just choose the meaning it usually has. The second thing you can do, you can imagine a prior past that tries to annotate words with their senses, do the best you can, and then represent. I mean, yeah, you're right. It is very relevant, and it's a problem. They ignore that. They just lumped it, you know, with the first, with the most common category, I suppose. The important thing is that now every word is represented by a string of bits, such that, remember we talked about the fact that even if you focus on questions concerning a particular word, there are a huge number of such questions. In fact, there are 2 to the 100,000 different questions that you can ask about a particular word, corresponding to, does this word belong to this particular subset of the vocabulary? Every question about a word, every binary question, corresponds to a particular subset on which the answer is yes. And therefore, there are 2 to the 100,000 such subsets. But we're now going to throw away the vast majority of these questions and focus only on questions that have to do with these bits. And furthermore, we're going to ask, because the meaning of the second bit is conditional on the value of the first one, and the meaning of the fifth bit is conditional on the value of the first 4, we're only restricting ourselves to asking about the identity of the next bit that we don't know. And there's only one such question. Is that bit 1 or 0? So every word in the history was represented by placeholders for the bits. Initially, none of them were known. And if you wanted to ask about this word in the history, you must ask about the first bit first. That's how you split the tree. You don't have to ask about this word. You can ask about a different word. But if you're going to ask about this word, ask about the first bit, the first unknown bit in that word. Once you ask about it, you were given the answer, let's say it's 0. The next time you want to ask about this word, you ask about the identity of the next bit. So you discover what the word is gradually. You learn gradually about it. You kind of shrink your space of possibilities. And now, if your history is long, say this is word I minus 1, this is word I minus, well, actually English is written left to right, so let's make it wi minus 1 is here. Huh. Okay. Once there was a queen. And now you want to know about this word, and this is your history. This is the actual history, but you don't know that. You're building you have a tree. You're going to ask about the first bit of the last word, wi minus 1, or the first bit of the one before that, wi minus 2, or the first bit here, 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 as far back as you want to go. If you allow yourself to go down the history of 20 words, you only have 20 questions to choose from. So the computational part became much, much simpler. At any one point, you're only choosing from order 20 questions.
But you're restricting yourself in the sense that you're not permitting yourself to ask questions about arbitrary positions anymore in the history,
Right. Yeah.
In that sense, isn't it some sort of a structured engram?
Yes, that is exactly a structured n-gram. It's a more refined n-gram. Instead of jumping in jumps of one word at a time, you're doing it one bit at a time. Well, it's a little more than that, because you can jump back and forth. And in fact, what they discovered when they ran the algorithm is that, not surprisingly, when you knew nothing about the history, the most informative word, as measured by mutual information, the most informative question would be the first bit of the most recent word. Just like you would have guessed that if you are asked, if you can be told the identity of one word, you would choose the last word of the history. It's the most informative one. The first bit of that word is more informative than the first bit of the word before that, and so forth. And after that, the next one would be the second bit here. And after that would be the third bit here. It really, really wants to know what's here. But at some point, it jumps to asking this question. And then it might jump back to here, and then it jumps back here again. And then at some point, it starts asking about this question. So there's a clear bias towards, the algorithm shows in its result, towards asking questions about the most common word, the most recent word. And after that, there's a bias towards the one before that, and the one before that, and the one before that. So it is significantly richer than an n-gram, because an n-gram cannot ask partial questions about the words. And here you're down to the granularity of a single bit. Bit here, bit here, bit here. And in fact, you can compare it to an n-gram. That's what they did. They figured it is fairly easy to represent an n-gram in this kind of formalism. So an n-gram is certainly part of the space that this search is in. And let's track the behavior of this tree, the performance of this tree in terms of perplexity, on some test set. So here's our goal. Our goal is the n-gram, the best n-gram performance. And you have some perplexity. And here's the performance of our tree. It starts with just being a trunk, so it's a uniform. It's very bad. But as you ask more and more questions, it goes down, right? And the goal is to not only reach the n-gram, but to go down below. And again, the algorithm was still very computationally expensive because they cut on the search here, but they allow themselves, so one thing, I don't remember exactly the details, you can check it in the paper, but because of the point you made that you can no longer ask about, is there a dog anywhere here, they allow themselves some other questions, other types of complex questions that combine these. I'm not sure. Actually, it's not in the paper. They never published it, which gives you a hint of what happened. So here it came, and it still took weeks, and never crossed, never got better. At which point they just said, the heck with it, and went home. So that was the sorry story of attempts to make trees work better than n-grams.
Do they always go to the previous word, or do they jump to some and they make gaps in the history?
I don't know. I'm guessing, since they used a lot of data, that it was fairly smooth. So you can calculate mutual information between the current word and word I minus k for any k, right? So I minus 1, I minus 2, I minus 3. And it's a if you calculate a large enough amount of data, so you can think about these as distance bigrams, where you predict the next word based not on the last word of the history, but a word a few places back. It's still a bigram because you're conditioning it only on a single word, but it's a long distance bigram. And if you do that, the mutual information drops very fast, and it's always decreasing. So if you look at the mutual information from the current word wi and wi minus k as a function of k, mutual information is very high in the beginning and then drops quite a bit and then drops more and then drops and then becomes, after, I don't know, after about 10 words, it's not 0, but it's pretty uniform. I did that once, many years ago, calculated based on a lot of data. So you're kind of asking about the correlation. It's not exactly correlation, it's mutual information. It's better, but you're asking, is there still correlation? Is there still interaction between the word and another word that occurred 17 positions before it? And the answer is yes, but not more than the word that occurred 15 or 20 positions before it. Can you guess what's going on, where this information comes from?
Topic.
Yes, it has to do with topic. So as long as you flush your history at the end of a document, and you allow the history to be as long as you want, there is still some residual information between any word, no matter how far back in the same document, and the current word, because they're all on the same topic. When you get close, there's significantly more information because of syntactic considerations and also more coherence of the topic itself, a subtopic. So to answer your question, I don't know specifically what they found, but I'm guessing that with enough data, it would be very gradual. You'd always prefer things that are closer, up to the same phenomena that I found.
Essentially, no gap n-grams that can be useful.
Well, they could be useful, but they are not going to be considered in a greedy search. This is a greedy search. So going back to the 3 kinds of errors, modeling errors, search errors, and Bayesian errors, I introduced them in the context of a classifier where it's very clear when you make an error. But you can think about it also in the context of density estimation. Why isn't your density estimation any better? Is it because you made the wrong modeling assumptions? Is it because you failed to find the optimal member of your set? You made a search error and there are better members? Or is it because that's the best you can do because that's the true entropy of the source? That's what the Bayesian error is. Which one of these 3 do you think is at the root of the problem of the failure of trees?
Guess is most strongly in favor of search errors, but it's possible that there is a underlying Bayesian error as well, which possibly affects n-grams, but also decision trees.
Okay.
I think it's a search error because I don't think that n-grams are the best type of tree model to comprehend language. I would still, as an unproven statement, I would still say that there's some tree that could be better than an n-gram.
I agree with both. I also think it's a search error. I think most people would think it's a search error. So we can rule out the Bayesian error. The Bayesian error in the case of density estimation corresponds to your model having reached the true entropy of the source, and it's not possible to reduce it any further. We know that's not the case because we have experiments with people, where people are asked to guess the next word in a sentence or the next letter in a sentence. They do better than language models. At least they did better last time they ran these experiments 20 years ago. So Shannon was the first one who ran these experiments, and that's why we call them Shannon games. And they've been repeated many times in the 70s and 80s, possibly in the 90s. I don't know how people will do today because we have so much data today with Google Ngrams that it's hard to tell. But way back then, people did better, and obviously people were not exposed to billions and trillions of examples the way Google is. So clearly people use other sources of information, and one of the most fruitful ways I think you can improve the state of modeling is to do these kind of games with people in a controlled environment where you expose them to some sources of information and not others. So the traditional vanilla Shannon game is you show people the beginning of a story and you stop it in the middle, either in the middle of a word or in between words, and you ask them either to guess the next word or the next letter. I mean, there are variations. But you show them everything there is in the past. And people are pretty good. And the thing about people is that they're not as good in terms of estimating probabilities. They're lousy as probability estimators. But they're very good at ranking possibilities, and especially at coming up with good possibilities. And what they use for that is far more than the last 2 or 3 words. To prove that, you can show them the last 2 words. You can pretend that they have the same access to the same information as a trigram. And they do worse than a trigram. But when you show them the rest of the history, they understand the story. They understand what is being said, and they can anticipate what will be said next much better. So they clearly look further back, and they clearly use a variety of syntactic constraints, semantic constraints, pragmatic constraints, common sense constraints, linguistic constraints. People have an incredible way of incorporating many, many different types of constraints or information sources or heuristics and bring them together. And we're not very good at doing that with machines. We are good doing with machines is optimizing the heck out of large amounts of data and coming up with good probabilities. I'll get to you in a minute. So one of the nice things you can do is do a controlled experiment with people where you expose them to the last 3 words plus only the part of speech of the words before that. Or the last 3 words and everything before it. Or the last 3 words and the topic of discussion. You can give them different sources of information and see which one of them helps and which doesn't help. It's not ideal because people haven't had time to develop intuition about this kind of half-hidden. But you can certainly imagine a situation where somebody listening to a conversation and they overhear some words, they don't hear all of them, and they make it up. So you can simulate natural situations like that. Okay, there were a variety of questions here.
I was going to say,
comments.
doesn't that imply it's more modeling error than search error? Because, I mean, we're coming into the problem with a much richer model of background knowledge.
Right. So, all right. So all I was arguing was that I'm removing the Bayesian error. There is Bayesian error. I mean, there is true entropy in English, but we are nowhere near having reached it with models. So now the question is it modeling or search? And that corresponds to the question of, are there better models that can be expressed as trees or not? If there are better models that can be expressed in trees, then there's definitely a search error. But there's also a modeling error because there might be even better ones that cannot be expressed as trees. And I think that's true. Imposing trees as a bias, as an assumption that it has to be expressed as a tree, does cost you something, in that there will be things that you cannot express, perhaps. But I think that there is also a significant amount of search error because I do believe, that's the same belief that Malcolm expressed, that there are trees out there. There should be trees out there that are better than n-grams. And we can probably prove that as well by exposing people, having people ask questions, right? Having people construct trees on the fly. I don't know if anybody has done that. So I do think all 3 sources are there, but I think the main reason for the failure was not because we're near the limit. There is Bayesian error, but that was not the reason we failed. I don't think we failed because the modeling was wrong. I think expanding from n-grams to trees is a powerful and appropriate extension, although it's not perfect. But I do think that we're still struggling with the search problem. There are just way too many trees, and we're not asking the right questions in the right order. So coming up with good questions might be a good strategy to try to beat that. When I say good questions, I don't mean the second or third step of calculating mutual information. I'm talking about the very first step of coming up with the trillion questions you're able to look over, rather than the 10 to the gazillion questions that you can never look at.
Just as a sort of side discussion, I think that the key, or the fact that a decision tree is a partition model, I think that would be the best. To argue that that is an incorrect assumption for a language model, I think would be the best way to kind of get some insight as to think, well, maybe this is all just a big modeling error. Because I feel a lot of times with language, like if I'm reading a sentence and if I was asked to predict the next word that was coming up, or even something like predict what's the topic of the next sentence, I don't think that I would make like a series of very discrete choices on just like the history of the words. I think my choices would have different like sequences of words that I would make decisions on, and those sequences could overlap.
I buy that. From a theoretical point of view, expressing things as a partition is not that bad. Well, let me start from the other direction. Partitioning, this is a comment I made at the end of the last lecture to somebody who came to me. Partitioning is problematic because it fragments your data very quickly. So if you build a tree, after you ask the first question, you've split your training data into two parts, typically comparably sized. And now you're going to split each one further based on decisions you make based on only half of the original training data. And then you ask another question here, another question here. Now you divide it into 4 sets. And there's no crosstalk between them. Whatever data happen to fall here is only going to be used here. They're not going to be used here. So very quickly after depth 10, after you develop depth 10 tree, you've now splintered your data into 1,000 different sets. Each one has 1,000th of the amount of data of the original corpus. So one of the problems with partitioning is that decisions based on a finite amount of data very quickly reach a point of dwindling data, and therefore they're unreliable. In a theoretical mindset where you have infinite data, the fact that you're in a tree doesn't reduce your expressive power, because you could still, if you have infinite data, you could still make the right decision. Or even if you don't know how to make the right decision is there. You just don't know which one it is. So using a partition-based model does not restrict your expressive power. But practically, given that you have a finite amount of data, it is a severe limitation. And one of the things we're going to do in the second part of the course is try to do away with the partitioning, so that you can take into account multiple considerations without fragmenting your data.
Does partitioning really make sense even in infinite space, especially dealing with language? Because coming back to the point that we made earlier, you're assuming that a word can belong to only one single point in your multi-dimensional space, whereas language doesn't really behave that way. One point may belong in multiple places in
Right.
space, and when you partition it, you restrict it to being one single
Right.
partition rather than
Right. So theoretically, you can solve that by summing over all possible combination of latent variables. So you have a history, and every word in the history could be one of multiple senses, and you have a very large but finite number of combinations of senses, and for each one of them you're going to solve the tree separately, and then you're going to combine them somehow, theoretically. Practically, of course, you're right. That is a significant impediment. Okay, let me move away from trees. Trying to think of the best way. Or move away from partition models, which is really the best way to think about it. One of the lessons we learn from this is that the representation you use practically makes a huge difference to the kind of questions you allow yourself to ask, and to the search that you're going to make. So here we're talking about, they came up with a very clever representation of words that makes sense. It incorporates linguistic intuition and syntactic intuition and semantic intuition and statistics, because they derive these classes automatically. And it doesn't take anything away for good. You can still represent every word, but you came up with a way of representing it that's hierarchical, so you can ask about its identity in steps, which is really, really nice. In general, clustering words together might make sense. Why would we want to cluster anything? Is it to help with bias or to help with variance? What does clustering do? So this is not clustering, this is representation. But suppose I clustered words of the vocabulary together such that This is my vocabulary. And I'm going to break it into non-overlapping sets, namely a partition of the space, such that I'm going to look at the history through a lens that tells me only what class a word is in, not what the specific word was.
Should be variance reduction.
It is variance reduction. The reason I'm interested in clustering in general is because I have a finite amount of data, it gets fragmented very quickly, it's not enough to make reliable decisions, or in other words, it leads to high variance estimators or high variance classifiers. So I'm going to coarsen my representation. Coarsen it as in making it more rough, less refined, less high resolution. I'm going to reduce the resolution of my representation so that my data falls into fewer categories. There are more data points in each category, and therefore I have more reliable estimation. Of course, the flip side of it is that I have higher bias. So consider the difference between probability of a word given that the last word was Tuesday versus probability of a word given that the last word was a day of week. Suppose we're interested only in bigram relationships. So we're only looking at the relationship between how the distribution of the current word depends on what happened before it. And we're considering basing it on the fact that we know that the previous word, this is I minus 1, based on the fact that we know that the previous word was Tuesday versus based that we know that it was one day of the week. If we had infinite data, we shouldn't go to here. We should stay with this. Because we're going to estimate this from some kind of count of how many times the word Tuesday was followed by that particular word, divided by how many times the word Tuesday occurred. Right? And maybe it's going to be smooth somehow, but that's going to be basically what I'm basing it on. The relative frequency of that particular word among all the words that came right after the word Tuesday. If I use this, the formula is going to be similar, but any day of the week, which means any of the 7 days of the week, followed by that word, divided by how many times I saw day of the week. And again, this would be smooth too. So which one would be better? If I have a lot of data, I'm better off here, because one could argue that the distribution of words following Tuesday may be a little different than its distribution after following other days of the week. Certainly, it might be different for Saturday and Sunday being kind of unusual days. But you could also argue about Monday. You know, thank God it's Monday. Thank God it's Friday. They're different. Black Monday. There are expressions that involve particular days of the week. So in the abstract, when you don't think about specific data, in the abstract, you're better off with this. This has lower bias. Lower bias. It is more close to the absolute truth. But this has lower variance because it is based on more data. So whether it's a good idea to lump them together or not depends on how much data you have. And as you have more and more data, you want to do less and less clustering. And the other way around, as you have less and less data, you want to do more and more clustering. And you might decide on the optimal point based on some held out data. In language, we usually need a lot of clustering because we're in a very super sparse situation. So the question becomes not whether we should cluster, but how we should cluster and how much. When should we stop? We can cluster in many different ways. Our original problem would say was to estimate the probability of a word given word I minus 3, word I minus 2, word I minus 1. This can already by itself be thought of as a form of clustering, where we took all the events that happened before I minus 3 and clustered them all into a single place, saying we don't care about you. So throwing away a variable or chopping the history can be thought of as an extreme form of clustering, where you clustered everything into one class. Namely, you stop making distinctions based on it. But I can change this to probability of wi given class of word I minus 3. And here word I minus 2, word I minus 1. So I only clustered the very furthest word in the history. Or I can cluster both this one, I minus 3, and this one, minus 2, but not this one. Or I can cluster all three of them. I minus 3, I minus 2, I minus 1. And there are other variations as well. I can cluster these but not these. It doesn't make much sense because I care more about what happens closer to the end of the history. But I could try that. And even within each decision to cluster and to condition it only on a class, I can decide how strongly to cluster. Do I take a vocabulary of 100,000 words and cluster it down to 10,000 categories? To 1,000 categories? To 100 categories? I can stop anywhere on the way. So there are a huge number of decisions, as you can anticipate, exponentially many decisions. Exponentially many choices. One nice thing about this hierarchical representation of the vocabulary is that if I decide that I want 1,000 classes, it's very easy to find a level in the tree that when I cut it, there are exactly 1,000 categories in it, or about 1,000 categories. So a hierarchical clustering of the vocabulary gives me the ability to decide on any number of classes and to immediately have a reasonable suggestion of these classes. There's another representation for cluster models that I'd like to make you familiar with, and that is the generative representation. The story, the generative story that tells you, oops, no, that's batteries, that tells you how the data was generated. By the way, when you cluster, the resulting models are called class-based or cluster-based models. So what I showed you there are class-based n-grams. So if I want to represent the full word-based 4-gram as a with some kind of a graph that describes the generative story, I would say there was a word here, wi minus 3, and there's wi minus 2, and wi minus 1, and then the word wi depends on I minus 1. It also depends on I minus 2 and I minus 3. These three arrows say that it depends on all three in some way. And then the next word, wi plus 1, will depend on this one, and this one, and this one, and so forth. I plus 2 will also depend on 3. That's a 4-gram. A bigram would look less messy. In a bigram, wi minus 3, wi minus 2, wi minus 1, wi. A bigram is very simple. It looks just like this. Every word depends on the word that came before it, and only on the word that came before it. So this would be the generative picture or graph that corresponds to the bigram assumption, to the assumption that language is a first-order Markov chain. What's the zero-order Markov chain? That's the unigram, right? Words are generated independent of any other word. What would it look like in a graph? No, it would just be the words with no arrows between them. No arrows. Each one is its own. Every word is an island. I'm sorry? Oh, forest. Sorry. Thank you. It is a forest. So I can represent word grams like that. Now let's look at class-based n-grams. How would I represent those? Well, it depends on the particular dependence. And I can create something here and then construct a graph. I can do the other way around. I can construct a graph and then represent it in an algebraic form. So let me do that. Suppose my story is that there is a string of classes or clusters and that it is the string of, latent classes that generate, that are the Markov chain. And then from each class, a word comes out. And so forth. This is a very clear and succinct generative story. It says that there's a stream of clusters, word clusters or word classes, and that they are generated based on the bigram or a first order Markov chain. And then each one of them generates the word. Now the visible part, at least the immediately visible part, are the words. But they actually don't generate each other. They're generated from something that is potentially latent, potentially hidden. And this is visible. Now, are these really latent? That depends on whether the classes overlap or not. If they don't overlap, we call it hard clustering. And if they do overlap, we call it soft clustering. If they don't overlap, knowing the word means that you know the class it came from, because every word belongs to exactly one class. If they do overlap, you don't know. This could belong to many more than one class. And these are then latent, and you need to somehow reason over latent variables and try to infer what they're likely to be. Either way, I can summarize this model in a form like this. It would be P of word I times class I times P of class I times class I minus 1. Because I only connected adjacent classes, this is a bigram model. There's no extra arrows. That's this. That's a bigram model. And since the word was generated only knowing the class of the same position, I have this here. If this is a hard clustering, this is no, in both cases this is a true distribution. But if in hard clustering, P of Ci given Wi is known, it's either 1 or 0. If it's 1, if it's the correct class of W, it's 0 otherwise. If it's soft clustering, it doesn't have to be 1 or 0. Now I can modify my model. For example, what do you think about this? That means the current word is determined not only from the current class, but also from the class before it. That would be written as probability of word I is given by C of I, Ci minus 1, and C of I. C of I minus 1 and C of I. I mean, one before and the same.
Also the probability of Ci given Ci minus 1?
If I put them both here, then that's it for Wi. I can say that Ci, so if I want the full P of word I, comma Ci, given the history, I can now write it down as P of Ci given the history times P of word I given Ci and the history. Right? This is just a chain rule. And now I know that P of Ci given the history can be written as P of Ci given Ci minus 1. That's the bigram assumption on the latent variable. And P of Wi given Ci has to be written as P of Wi given this depends on Ci and Ci minus 1. So that's what you meant. You're right. I mean, if I start from figuring out both of these. So I need to figure out, you're right, I need to figure out in every step both of these. And that's how we do it in this case. In the case of when I didn't have these arrows, I will rewrite it. P of Wi and Ci given the history. First I break it down the same as here. P of Ci given the history times P of Wi given Ci in the history. But now it's going to be a little different. Ci given history is still the same. It's P of Ci given Ci minus 1. So we still make the bigram assumption on the classes. But here, not having the diagonal arrows means that this is simply P of Wi given Ci. I don't need the rest. Whereas here, I do need the rest. So you can see how you can write, and I'm glad you pointed it out. I need to start with this full thing, not just with a single word. How do I generate both the word and the class together? I need to factor it and to explicitly state its dependence on different elements of the history. That corresponds to particular arrows here.
The number of classes are, I mean, they're the same as the number of words? They're unique classes or?
No, they're not. They don't have to be the same as number of words. So when you talk about the number of classes, you mean when you take your vocabulary and you break it into sets?
Yes, because you have like word I, like Ci mapped to word I, Ci minus 1 mapped to.
So I ran a little fast. I should have been a little more careful. When I say Ci, it is simply a shorthand for the class of word I. So word and I here is not an index of how many, but is an index of position in the sentence. But you're right that every one of these C variables is identifying one of these sets in this big in the big partition. And the partition could have 10, 100, 1,000, any number of members. Smaller than V, of course. But
Oh, did I get it correctly that on the previous picture when you had errors from Ci minus 1 to Wi, so you intentionally like didn't use the errors for Ci to Ci minus 2. I mean, that's all.
this one,
Yes.
I can do that.
Okay, so it's
we
just
can-
a choice.
Yes, it's my choice of modeling. What I'm saying is that it opens a very large space of modeling assumptions. One way to think about it is, where do you think the dependence really is? So I gave an example here. Let's go back to the example. Do you believe that the distribution of the next word depends on whether this is Tuesday or is it the same also for Wednesday, Thursday, Friday? If you believe that they're the same, then you should always cluster them together. If you believe that they're different, well, then it depends on how much data you have. Do you have enough data to see the difference? If you have moderate amount of data and there's some difference between them in the frequency with which they occur after Tuesday versus after Wednesday, do you think that difference is because of random fluctuations in the sample? Or do you think that difference is because they really are different? If it's because of random fluctuations, you should put them together because you will reduce your variance. If it's because of true difference, that you shouldn't. You can estimate the variance using a variety of techniques based on the amount of data you have and sampling, but it's impossible to estimate the bias. Well, you can estimate the bias, but it's impossible to estimate it accurately. You can get to a point, I'm sorry, I shouldn't say that. You can estimate it, but there's a problem there. So you can look at the distribution after Tuesday, the distribution after Wednesday, and ask yourself, these are finite distributions of samples, ask yourself, are they likely to have come from the same source? And say the chi-square test would give you an answer to that. The problem is, so this is why I took it back. The problem is that in language problems, anything that you subject to the chi-square test will come back as significant. Because the chi-square test As soon as, because there's so much data, I know I said before that we don't have enough data. It's true too. We have a lot of data, but it's never enough. Because you're basing the chi-squared decisions on a lot of data, even a small difference between the distribution following Tuesday and the distribution following Wednesday will result in a very significant chi-square statistic. It's very significant statistically speaking. It may not be significant practically speaking. There's a difference between statistical significance and real-world significance. So an example would be, let's look at one particular word following the word Tuesday or following the word Wednesday. Let's look at the word, my favorite example word is Brazil. I don't know why. Brazil. Let's say for simplicity that Tuesday and Wednesday both occurred in the training data the same number of times. They both occurred 10,000 times. So count of Tuesday is 10,000. Count of Wednesday is 10,000. Of these, Tuesday was followed by Brazil. No, Brazil was followed by Tuesday. No. Tuesday followed by Brazil. $40 times. And Wednesday, let's say 50 times. You can give this to a chi-square test, and it would tell you, it wouldn't tell you whether they're the same or not. What it would tell you was, if they both came from the same distribution, how likely are you to see this kind of situation? Now we need to talk separately about hypothesis testing. But it would tell you, if you make the assumption, what's called the null assumption, that they both came from this, that the true probability of Brazil is the same under both conditions, how surprised should you be with what you see? And if it tells you that you should be extremely surprised, then you should say the null hypothesis failed, and they're not the same. It doesn't tell you how similar they are. And therefore, it doesn't quite answer for you the question of should you put them together or not. Are they different? Of course they're different. Anything is at least slightly different. And with enough data, it will look statistically significantly different. The question is, how different is it? You know, your best estimate here would be 4 times 10 to the negative 3, so 0.004. And here it would be 0.005. Are you better off putting them together for the future? And you can try to make decisions based, again, on held out data, make some global decisions. In general, I don't believe that clustering based on the data would give you significant advantage. In fact, many people tried to do a variety of clusterings based on the data. And the problem is, as I see it, and this is a bit of my personal view, is that you can't get something out of nothing. When you try to cluster words based on their core occurrences in the data, you will find that words that are, if you try to assess how well you did by your linguistic intuition, by looking at the result and say, does it make sense? Oh yeah, it put Tuesday and Wednesday together. It also added another word that has nothing to do with it. I don't know why, but it did. I will show you examples of that. And what happens is, words that occur enough in the training data to be reliably clustered will be clustered well together. You'll make the right decision about them. But if they occurred enough times to be reliably clustered, then they don't benefit much from clustering. They will do fine on their own, thank you very much. The words that stand to gain the most from clustering are those that occur very few times. So they will do very poorly on their own. But because they occur very few times, your clustering decision, where to put them, is very unreliable. And we see this again and again when people try to cluster vocabularies. You see these beautiful classes. It's a wow, how smart. Automatically, from a lot of data, it figured that Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and Monday are all in the same category. And Casablanca is in there too. I don't know why. Well, you check to see that Casablanca occurred only twice, And that was the closest mutual information measure, so that's where it put it. The sad thing is that Casablanca occurred only twice. You just don't know enough about it to say that it's similar to other words. I'll get to you both in a minute. The one exception is if you can cluster based on some other data that is maybe much larger, and you believe that the same clustering occurs in both domains, then you can use the large amount of data that you have that's relevant for clustering but for some reason not relevant for modeling, or if you bring your domain knowledge in. So one successful example of clustering appears in a very small domain. In the 90s, we worked on a dialogue system, automated speech dialogue systems that would behave like a travel agent. You would tell them, I need to book a flight from Boston to Chicago on such and such a day, and it would it would convert into a query, it will recognize it, convert it into a query, give you an answer, interact with you, very nice. When we built the language model for this, we defined classes in advance. There was a class of all cities. There was a class of all times, like 3 p.m., 4 p.m., 5 p.m. AM and PM were their own class. You were allowed to ask about whether they served breakfast or dinner or lunch. All these words, breakfast, dinner, or lunch, were in the same class. Departure and arrival. I mean, you knew the domain. It was a very limited domain. And we knew a priori coming in that some of these words are interchangeable, that anything you can ask about Dallas, you can also ask about Austin. So we created those classes then, and that allowed us to build a fairly good language model with very low perplexity from relatively little data. So if you have domain knowledge, classes are great. If you have huge amount of data that's outside but you believe has similar relationship, the words have similar relationships, it works. Otherwise, using the same corpus to both train the clusters and to train the model, I have not seen work, and I don't believe will. Several questions here.
Could you use it to do like smoothing at more of a sort of, I guess,
Sure.
fine-grained level?
Sure. So you can, just like you can choose at what resolution to make classes to balance bias and variance, you can also take whatever you chose and smooth it or shrink it with a word model. The full word model is an extreme case where every word is in its own class, right? So combining the two is another form of trading off bias and variance. Yep.
So yeah, knowing the size of data we have, shouldn't we know a benchmark or limit of how much mutual information between adjacent classes we should have for the estimation to work?
What do you mean by mutual information between adjacent classes?
Like, I'm assuming that mutual classes, adjacent classes should have the optimal mutual information for the estimation to work.
By adjacent, you mean consecutive in a sentence?
Right.
Okay. I try to keep the discussion until now very general, all kinds of clustering that you can do. But now let's make it, by now I mean Wednesday, let's make it a very concrete discussion. Let's talk about only a bigram model. So we're going to make it very, very simple. We're only talking about a bigram model, and we're only talking about, in fact, a specific kind of model, which I will write now in a graph form. It's this model. I'm not going to put the indices. So there's a set of classes that moves forward as a Markov chain, first order Markov chain, and then the words fall off of them. And I'm going to make the further assumption that these are hard classes. So knowing the word, I know the class. And I'm only going to ask the question, what's a good way to cluster the vocabulary to get the best such model? And that leads to your question. Yes, you're looking for clustering that maximizes the mutual information between adjacent, what you call the adjacent classes. So if you haven't yet read the paper that comes with the lecture, please read it. They go into a lot of detail, and especially if it's hard for you to follow what's going on, it's a great way to give your mind a head start to cover this topic, and then we will discuss in class what they did. Okay? Thank you.